This is the derivation of the speed of a pulse on a linear medium, or in other words, how fast does the wave travel on a string, the calculus version. So if I have a tight rope right here with some tension pulling on it, I know the tension is constant throughout. We are assuming a certain amount of idealism. And I put a small little, I pluck it, and I send a pulse on. So I basically create a pulse in this, which is traveling at some speed v sub x. Let's establish a coordinate system of x and y. So this pulse is moving off to the right. What I want to do is I want to zoom in on just this little piece right here, the point where it's starting to lift off the ground. So if I look at that piece right there, some angle theta, this is lifting up at a speed v sub y. And it's an infinitesimally small piece, so this section right here is the length of d sub x, and this right here is d sub y. We have a couple of different relationships involved here. I have Vx going to the right, Vy going up. I know that Vx is going to be the rate of change in the x direction with respect to time, and Vy is the rate of change in the y direction with respect to time. I have a relationship here. I know that the tangent of theta is equal to the opposite over the adjacent, so dy over dx. We have a, because I can turn anything into a right triangle, no matter how small theta is, as long as theta is not 0. And so I can come up with a relationship with dy dx, because that's going to be equal to dy dt times dt dx. We can always cancel the dt's and get back to where we started. So dy dt is vy times the reciprocal of dx dt, which is vx. And so I have that vy is equal to vx tan theta. And don't worry, the theta is going to go away at some point. If I now look at the forces involved on this piece of string, I have a tension that is acting off at an angle. And since it is traveling at a constant speed in the horizontal direction, the only force that really is going to matter here is the vertical one. So that is going to be Ft sine theta is the vertical force equals Fy. And so I think that we've set up the basics here. Oh, one more thing to set up the basics. We do need to look at the linear density. So mu is the linear density, and that's equal to the mass over the length, or on a really small scale, dm dl, or in this, given our convention right here, dm dx. So now let's take a look at the impulse. Impulse is equal to integral of f dt. It is a vector, which is equal to the change in momentum. If we look at the differential of that, and I'm just going to drop the vector symbols for ease because I'm going to forget it at some point, that's equal to f dt, which equals dp. So the force that is being applied here is in the y direction, so that's f sub y, and so this becomes the change in dp sub y. And so I have Fy dt is equal to dm vy, because we're dealing with the impulse in the y direction. And that is equal to v sub y dm plus m times dvy. The change in v in the y direction, well, if v in the x direction is constant and that angle is maintained there, then the change of the speed in the y direction is close enough to 0. And so what I'm left with here is Fy dt is equal to Vy dm. Fy is equal to Ft sine theta. So I have Ft sine theta dt is equal to Vy, and I know Vy is Vx tan theta dm. Now, using the small angle approximation, we can simplify that one step further. So we have Ft sine theta dt is equal to Vx tan theta dm. So small angle approximation, if theta is much less than 1, then sine theta is approximately equal to tangent of theta, which is approximately equal to theta. Anyway, these two are close enough to each other. So what we're left with is the tension in the string dt is equal to Vx dm. So the tension is equal to Vx times dm over dt, which is Vx times dm dx times dx dt. That's just the speed in the x direction, and that is the linear density of the string. So this becomes Vx mu Vx, or Vx squared is equal to the tension over the linear density, or the speed in the x direction is equal to the square root of the tension over the linear density. And so a second derivation, there are other derivations that I have seen, but I'm going to stop it there.